I
Yes,
will
yes.
do
I
it.
don't know anything about it.
Yeah. Hello everyone. Today's session will be taken by Kanav, who got like India gold medal this year. And yeah, he reached very high height by India gold medal. He like geometry a lot, and he will be taking like different type of session on NT construction. And hope you will enjoy the class. Yes.
Yeah, so I'll start. So what exactly is construction NT is you will be given a statement of the form prove that there exists infinite positive integers or something satisfying a certain property. So I decided to divide it into two parts. The first being something called the CRT force. So, and the second part is something different. Also, I'll prefer if you want unmute and say that's much easier than reading chat. Anyways. So the second part, I'll tell it later. So the first part is the CRT force. Now, why did I call it like this? Because CRT is just too strong. So I think, okay, do all of you know what CRT is?
Yes, the Chinese remainder theorem.
Yes, great. So basically, I can just like there exist numbers with any residue modulo any numbers. I can choose any amount of AIs, any amount of RIs, just the condition that you need to ensure is that AI and AJ are co-prime. Now, this is just very strong that you will see. So I'm assuming people have some idea about constructionality. If you don't, I can start with simpler problems. But if you do, I can do slightly harder things. So do people have an idea have people seen a problem which uses CRT on a
I
construction?
have at
Yes.
least.
Not really.
Okay, so
I think like 2000 IMOSL N1 counts.
I don't remember the problem.
It's like you have to find all n such that A is equivalent to B mod n if and only if AB is 1 mod n.
I don't remember.
Okay.
Okay, anyways. Let's just do it. Let's just do one problem and then we'll figure out how things work. So some of you might have seen this problem. If you have, a lot of you have, I'll just move to a different one.
Yes.
So
This is Amy, I guess, right?
no,
Not Amy.
it's not any problem. Okay, have a lot of you seen this problem or have most of you not?
I haven't.
I
Okay,
haven't
great.
seen it either.
Great. So great. So try this
Yeah,
problem.
I've seen it, but I forgot the solution.
No problem. So okay, try the problem and like at any point if you get any idea, feel free to tell. I don't expect you to solve the problem in like 5 minutes. So what the problem says, I'll just read through that. Positive indication is called beautiful. If for every base representation, consider the integer 2023 in this order. I mean, of course, that's not relevant.
If we get one solution, then why can't we just add 10,000 factorial to the power of some huge number to get a different solution?
That is indeed a good idea. Okay. So what did you say? I'll just say. So you start if you have some nice beautiful number, let's call it n. Now you want to add 10,000 factorial. This is some big power. Why
Yes.
does this help?
Because it is just a string
Because
of
like
zeros
only
in
the
all digits.
left digits change, the right digits don't change a lot. So
Precisely.
2023 is preserved.
Yes.
Right. So if you have this beautiful number n, if you look, let's look at a base v representation of n, looks something like blah 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 something. Now this 1000 factorial, this base b representation, will look something like a bunch of zeros out here. So when I'm adding, I can just safely preserve n in the last digits, and whatever number just comes here is something I'll just like present it. I have complete freedom over. Does this make sense? So I can choose some big enough exponent right here. Like I'll just call it big. So I can preserve my previous construction, and the beginning digits, I have some amount of freedom there. In this case, I don't know what the beginning digits are, but I can multiply this by some constant k, the free constant, let's say, which will give me some sort of freedom. Does that make sense?
Sure.
So like 1,000, if I just start with this number to the big, I do not have any control about the first digits. Now multiplying with this constant of k, I have some amount of freedom on how the first digits would behave. Some control I can generate while preserving the previous 2023 thing. Okay. What should we do now? So like, first of all, how do we even find one number?
Assuming it exists, it's possible that we don't have any.
Yeah, so okay, what we've proven is either there exists one, either there exists infinite, or there's nothing.
Yeah, so we
Right.
need to just find one. That's the
Yeah, but that's slightly tricky.
yes.
But like, why would we think that there exists such a number to begin with? Why won't we intuitively think that there exists no such number and try to prove that in some sense?
You have way too much. Okay, yeah, that's a good question. Also, someone in chat has actually just told a solution, but let's. So why would you expect the answer to be infinite or finite? One intuition is like, you have way too much freedom. Number of numbers which contain 2023 are a law. Majorly, if a big digit number, you're only fixing 4, it's very small. You have way too much freedom. But like most numbers actually contain 2023. And so if you have a big set and you're taking another big set and you're taking their union, you expect some element to lie in it, right?
Okay, yeah, sure.
And even if you do this like 10,000 times, the sets are so big that you would expect numbers to lie in the sets. So there's some intuition that such numbers would exist, and we just proved that which exists, there are infinite of them.
Okay.
And there's a perfect solution in chat. So it says that the exact thing that we're doing right now, we can do it step by step. What does that mean? Is that we start with just base 4 representation of a number 2023 in base 4. So this corresponds to some number, let's call it n1, or like, no, let's call it n1. We start with a number which does it for base 4. Now, let's do it step by step. So let's just do it for 4 and 5. So let's try to find a number n2, which works for 4 and 5. How do we do 4 and 5? So similar idea. I take n1, I add say 1000 factorial, 10,000 factorial, some exponent, big, and times my free constant. Now, why is the free constant helpful?
Then I can force the like starting digits to have a 2023.
Precisely.
How do we know that you can force the starting digits to have 2023?
Yeah, so once again, I'll just come to that. So we can choose k so that the starting digit works out. If we can do this, we're happy, right? We can inductively keep on doing this and get any number. So this is our only thing that we need to do. If we can do this, we're done. Does this make sense?
Yes.
Great. So how do we do this? How can you ensure 2023 to appear in starting digit? Like some amount of digits,
Can we just take again take k very very big, and then every increase in k will not have much of an effect on the first few digits, right? So every increase in +1 in k will have at most +1 effect on the first few digits, and we can just do
Perfect.
that incrementally.
Perfect. That's completely correct. There are actually a lot of ways to do this. So you don't really need to ensure the first digits. You can also work in somewhere in the middle. So one idea is to do CRT and for somewhere in the middle. But what Shreyan said is also a perfectly correct idea. So what he's saying is because I have my 10,000 factorial to the big is a very huge number. See, let's make it very huge. And when I'm slowly changing k, the first digits don't really change much, right?
Yeah.
Like, sorry, I should have said like k times this is very huge. And compared to 10,000 factorial to the big, I can choose k super large that this is basically nothing compared to this. Does this make sense?
Sure.
And so because I have a very, very big number and I'm adding a very small number out here, the starting digits are not really affected a lot.
No, but we're multiplying k to it, no?
Imagine you are increasing k step by step. Imagine you start with a absolutely crazy large k and you increase k by 1. What happens to the number k times this number?
Okay, so
You
like
add
K is also big.
k is huge. K is very huge. So I'll just write it. You start with a huge k. So that you get this is very huge. And now you're adding some fixed number, right? A very smallish number. That doesn't affect the starting digits a lot. So does this intuition make sense? In some sense, you should be able to hit every possible starting digit after a certain point, right?
Yeah, makes sense.
So do you want me to formally prove that? Because it's not really NT construction right here. Like it's like normal NT stuff. So if you do you want me to prove that, I'll do it. Otherwise, we can like move.
Yeah, please do.
Okay, I'll want me to do this. Fine. So you want to let's call this number m. So you want to show km has 2023 as starting digits. Okay, so if it never has 2023 as starting digits, so for a huge k, you can find some let's call it L, some LM which starts with say 2022, right? Something, and L plus 1 times M, which goes to 2024 times something, right?
Wait, how can you say we'll have 2022?
If you don't have okay, right? If you okay, so let's not say 2022. Let's say something less than that. Okay, something less than 2022 it starts with, like at most, and this is at least fine. This is fine.
Yeah.
So basically, LM is at most 2021 9999999, or like 2022 99999, and L plus 1 times M is at least 2024 0000000, right?
Yes. Yeah.
Now you just subtract them. So you must have M is at least some very big number, right? Very big. Because the number of digits of LM goes arbitrarily large. M is like a fixed number. That's a contradiction. Does that make sense?
Yes.
Yeah.
Good. Right. So that's it, went very fast. And that's it, we are done.
Wait, what was the contradiction again?
The point is LM can get very large digits, right?
Okay, yeah.
And difference of these two numbers will also get very large.
Yeah.
Does that make sense?
Okay.
Like it's at least like 1 0 0 0 0 0. 10 to the k minus 4 if the distance. This is bigger than 10 to the digits minus 4. And the digits can get very big, so this should be a contradiction. Does this make sense to everyone? I probably went very fast, so I'll repeat the entire argument. So what we actually did was we didn't use CRT anywhere, but we basically, in some sense, had so much freedom, we could just add in as many conditions as we want and just be happy with it because there are way too many positive integers. So our key idea was throwing in 10,000 factorial, taking it to a big exponent doesn't alter the base last digits of the base. And then we had some free constant which changes the first digit suitably, and we can maintain a structure going to a higher number. So this proves that if we can find one number, we can find infinite. So all we need to do is find one number. Now we do it step by step because let's do it for 4, then we'll do it for 4 and 5 and so on. So starting with 4 for 4 and 5, again, the same idea comes in. We try to start with some number having the structure. We try to add the 10,000 factorial, take it a big exponent, do our thing, so that we preserve the structure that we previously have. And the point is we can make numbers as large as possible. That's not a big problem because there are larger numbers. So basically after adding this 10,000 factorial to the big times k, we have some freedom about the initial digits. And the rest of the solution is more like details. So basically, even if we chose 10,000 factorial to the big is already a very huge number, we can still choose k, which is a bigger number. So even though the solution might seem like kind of like fishy that you're just choosing big numbers dependent on big numbers, we can actually do it sequentially and there are very, very big numbers. So everything is fine. So did that make sense to everyone? Or did I go fast again?
That makes sense.
Yeah, made sense.
Great. So great, that was pretty fast. Let's do another problem. See. Why does not work? It's not. So this problem says you want to show there are n consecutive integers a plus 1, a plus n minus 1, all of which have this random property that the sum of digits of any of these a plus I does not divide a plus.
Wait a second. So we can't just have a multiple of 3 there.
You can't have a multiple of 3, why not?
The sum of digits of a multiple of 3 is divisible.
You can have
by
other
3
prime
mod
factors.
9 can be divisible by 3 mod 9, for example. So
Yeah, I think
just take like 3.
No,
Just
but there will
three.
also be other factors.
If you
Yeah.
take 39, then 39 is not
300.
divisible by
No, but
12.
it's not.
So-
It doesn't have to be true for all of them. We just need to take
right,
find
right.
a few a plus I such that it's not divisible.
Makes sense, makes sense.
कपड़े चेंज करना है बेटा अपने चलेगा हमारे साथ पार्टी
मुझे उस दिन से सोई थी मैंने बेल्ट खोला उसके बाद barely आया वरना पैंट में हो जाती बेल्ट
just an example for a number divided by 3, for example, 99. Sum of digits 99 is 18, and 18 does not divide 99.
Yes, got it.
I mean, one thing that I would try to do is I would probably look at some starting numbers and I'd try to see which stretches among the initial few numbers like kind of satisfy this. And if
Good
there's a
idea.
neat pattern in some of those, I might try to prove that.
Good idea. Good idea.
One more thing is that a intuitive thing is that for a large n, there will exist some examples like 1 or 2 or 2 or 1 that are multiples of 3 and whose sum of digit will be 3.
Huh.
So you can't have n that like there will be some constructions in n like intuitively
Yeah.
because like for example, if you have n equals like 100 and you have it among the first 100 numbers, then you will find suppose 12 that has some of digits 3 and it's also divisible by 3.
Can we do something similar to last thingy? Basically, what we can do is we can say, we can start off with like a factorial of I into some 10 to the power of something, and we just push it back, right? And then we can add 1, 1, 1, 1, 1, and we can do something based on that. We can, if we somehow make this not divisible, so we have series which are all divisible by a plus I. So if we somehow add 1 to it, we can make it not divisible by a plus I.
You should repeat that. That went like quite fast. I'll just write it down so that should be fine. What did you just say?
Basically, we can first make a series which is divisible by a plus I, and then we can add 1 to it somehow.
Okay. Okay. I see what you're saying. So you're saying if I can find something like S of A dividing A, I go S of A plus 1.
Not a plus 1 necessarily, but kind of.
Some constant shift here.
Yes.
Like don't raise hand, you can just unmute.
Okay, so one thing that I'm thinking of, I'm not sure how easy this is to do or implement, is if we can make sort of the prime factors of each AI to be somewhat scarce, and in that they'll all be close to square root of AI, then we'd expect the sum of the digits to be much, much lesser than square root of AI intuitively. So that would automatically contradict everything.
Correct.
That seems like a hard thing to do.
That is a tricky thing to do. That is a tricky thing to do. And in general, if you have consecutive integers, you also have 2 other factors that just like
Right.
small prime factors would occur. But that's a good idea. Of like looking at prime factors. So like Athar, you're saying something.
Yeah, so my idea is like we have n, right, n consecutive digits. So we take something an n 10 to the k, which is way, way larger than n, and then we consider 10 to the k plus 1, 10 to the k plus 2 to the 10 to the k plus n. Now the main thing is that the sum of the digits of 10 to the k plus n will be 1 plus the sum of the digits of n. Because you have one very far away. So the thing is, if I think because of the divisibility, say it's not possible, we want each of the sum of 10 to the k plus I to divide si plus to divide 10 to the k plus I for some of the i's. So like I'm thinking if we take k arbitrarily large, there's so many divisibility constraints that will have to be satisfied. So like I think that will get us to a contradiction.
It's a great idea. So both of these ideas are actually combining them leads to a solution. So yes, that's a great idea. So basically, when you have digits, the spacing idea is very neat.
Do you just take like n random consecutive digits and then multiply by a factor of a power of 10 so large? And then divisibility cannot hold for each power of 10. Like after multiplying by a power of 10, we add 1 or some constant.
Okay, so you are trying to combine the previous idea as well. Okay. But you're saying if I start with some number a, I go to a times 10 to the k plus I. So I'm actually looking at s of a times 10 to the k plus I. This is equal to s of a plus s of I. And you do not want this to divide. A times 10 to the k plus I. You can choose some happy k which works out. That's what you're saying.
Yes.
Right. That is valid. Yeah, there are a lot of ways to do this problem. I think this might need some amount of effort, which all falls down to some the similar idea. So how do we force all these divisibilities to not hold? Is something that we need, right? We want some way to make all of these divisibilities fail. How do we force that?
Okay, so we
This-
choose I according to if A is divisible, then we choose that I is not divisible by A.
I you cannot choose. I varies from 0 to n minus
No,
1.
like, we can just choose I, right? I mean, like we add another constant.
You're saying you add another constant. Okay. So you're saying s of a times 10 to the k plus c plus I.
Yeah.
So then you get another factor of c. Yes, you can do that as well. But it's how do you force all of the divisibilities to fail simultaneously? Like there might be some set of k's. Say you get one divisibility constraint which fails for even k. You get another divisibility constraint which fails for odd k. Both of them can't hold simultaneously, right? One of them must hold.
Maybe
Does
you
that
can
make
take
sense?
product of first few primes, few matlab, not few, but like large amount of primes. And the sum will grow logly and the product will grow exponentially. So the product will have more digits than the sum will have value, right?
Right.
So we can just have
Right.
that the sum is small, sum of the digits of the product is smaller than the largest prime you're multiplying. Can we have that? And then we can just add one and then we are done.
What if we choose C that its digits also come out separately, like between the digits of and A into 10 power K?
Yeah, we'll do that only. So like basically you can add any amount of numbers initially. That's some idea. So okay. So
I
basically
didn't
what
understand Shreyan's argument. What was he?
yeah, I'm not following that either, so I just wanted to ask that again. But just to say this Shreyan's argument right here, and what some other person was saying as well, was basically if you have some I can add large powers of 10, a bunch of powers of 10, to make the sum of digits go like anything. That's anything I want. With all of these exponents being freedom. All of these exponents being totally free and has complete freedom over them. Okay, yeah, I didn't follow Shreyan's argument either. So Shreyan, could you just repeat your argument? Just write it down again.
Basically, the second one, right? The
Primes one.
Yeah. So basically, I would take the first product of the first large first n primes, right? And I take
Yeah.
it such that the sum of this thingy,
The sum of
p1 into
sum of
p2 into digits of sum of digits of p1 into p2 into pn.
this thing.
Yeah. No, sum of digits of p1, not separately inside multiply, but multiply.
Acha. The entire sum of digits.
Yeah.
Fine.
Is smaller than pn. If I can.
Oh, you want this?
Yeah.
This is insurable, I believe,
But
because
we
this should
also
behave.
need to ensure that it's less than P1.
I'm sorry, could you repeat that?
We also need to ensure that it's less than P1, no? Or does it suffice to show that it's less than Pn?
Oh, like he just we can find this for sure. How do we do after this?
After this, what we do? Then do we just take p1, p2, pn plus 1, plus 2, plus 3, plus whatever, plus I.
Why does that? Oh, you're saying every prime is bigger than Pn if it divides it, because none of the smaller primes can work out.
Yes, exactly.
I see.
No, so the difference has to be greater than I. No, sorry, I did not have to put smaller pn plus I. Great, something like that. Something. Sorry about that. Basically that.
Okay, Pn plus I would be bad, right?
Yeah,
So
pn
what
minus I.
is?
Sorry.
No,
Something
what
like
I'm
that.
saying, see, what will happen? What issues can happen out here is that if you start with any number a, one of a or a plus one must be even, right? So like you will have smaller prime factors disturbing you. Like smaller prime factors would divide these numbers, and you will have smaller prime factors disturbing. But that is a very, very nice idea. What you're trying to force is that some prime factors just don't divide, right?
Yes.
You don't want to force every prime factor to don't divide. You just want one prime factor to not divide. So all
Exactly.
you want is some prime factor dividing S of a plus I, and P not dividing a plus I. That's all we
Yes.
want to ensure for every I. If we can ensure this, that's it, done.
Yes.
Does that make sense?
Now I feel like we could do something with Chinese remainder theorem. Like we choose the E in a nice way so that modular conditions.
Yeah, perfect. So this is exactly what we'll be doing. So basically all of these things that we were trying to do initially, trying to add constants and like trying to vary case that divisibility doesn't work out, all would inherently need this argument. Just because we want to force all of the divisibilities to fail, we just do this very nice argument. We force Pi to divide S of a plus ai and Pi to not divide a plus I. We choose this for all I. Okay. Now the variable thing, the free choice that we have is A. Primes, no. We won't choose primes free. That's hardware.
Like
So
for A, we can maybe no that maybe something like factorial plus something, because then we'll get. Wait, why aren't we done with the 10 power thing argument?
we will be done now by the 10th power thing argument. Like the thing is that I'm trying to say is what finish would you do? Like if you see the 10 power argument, the way to finish the argument would be to force all of the divisibilities to fail simultaneously.
Could we
That
not
makes
like
sense?
just add a constant that does not affect either sequence and just comes up like changes the zeros in the middle, and we just choose the constant to be like product of primes which are not divisible by AI. So like if AI is divisible by SI, then we choose the constant not divisible by SI.
Yeah. So you're doing individually. How do I do it like fully, all together,
You
simultaneously?
just multiply those numbers, right?
What you're saying is that if for some a plus I is S of a plus I divides a plus I shift it by a constant, right?
Yes.
I find some C so that this happens to be true. And this somehow doesn't divide a plus I plus C. This is what you're saying? S of C.
Yeah. Okay, I
Now,
see.
when I shift this C, the other numbers will also be fixed by the same C.
Okay, yes,
right?
yes. Yes.
So if you want to inherently try to, like if you want to try to stop all of the divisibilities, almost every argument would use something similar to this.
So we need to have a condition on the primes.
Not the primes. That's the best part. You don't find any condition on the primes. Primes are harder to control. You let the primes flow freely. The conditions that you will ensure are on A.
Oh, right.
We just wanted some consecutive. So we just blindly throw every possible residue thing on A. And because CRT does our job, we literally don't care about what exactly the number A is. We just go ahead, we force, so like the CRT force A to be something mod PI, something mod blah blah blah. For a million conditions, you don't care. CRT cares about it. We don't. So like you can force as many random conditions as you want, you'll be fine. Just because primes are co-prime to each other, life is nice. So the only thing that you need to ensure right now is how do you force all of these things? Like somehow this is all you need to control, right? But again, by all of these things that we've been doing ahead, you can choose anything I want here. And these exponents, you can vary. Like you can choose them. So I'll just do the argument formally. So this is just formally, like the entire intuition of the part is done. Now you just need to formally like do things. So assume the numbers that you choose look something like this. So wait, let me slow down. Is everything clear till now? Like what I was trying to motivate and
Yes.
Yes,
like to
quite
everyone.
Yeah.
Was I going too fast? Was I going too slow? Did I feel
No,
like
it's
I've
all
gone
clear.
fast? Great. So the numbers that I'll be considering look something like this. This I where I varies from 0 to n. Now what we want to ensure is like I'll give you prime, so I'll choose some large primes. I don't really care. E1 to Tn. such Pi divides S of, we call this A plus I, which I can just say is S of I plus N, right? That's fine. So all I want to ensure, so condition on L is just congruent to minus S of I mod Pi. Now this, like, I have so much freedom. CRT just lets me write any sort of these congruents and I can find an L. Like, I don't care how absurdly large L is. I don't care how absurdly bad looking L is. There exists one, I'm happy with that. So I found an L, like, for all I. So found L.
So we're kind of using the generality of CRT too.
Yeah, exactly. You're just using, like, CRT gives you too much freedom, and I'm like, I'm happy with that. Just spam that as much as you can. Now what we need to ensure is Pi does not divide A plus I. How do we ensure this?
I mean, we can first order the Ki to be divisible by P1 to Pi. No, not
Yeah,
like divisible by Pi minus 1.
Yeah, perfect. So what you can show force is, like, now A depends on these KIs. You can choose PIs to be not 2 or 5. So you can force more CRT forcing. Pi minus 1 to divide each of the KJ. You can do this. So now A is just congruent to L mod Pi. Right? Now you want to ensure Pi to not divide L plus I. I'm sorry, something.
How did you get Pi A congruent to L mod Pi?
Yeah, okay, good. I'll repeat that. So my A was 10 to the K1 plus 10 to the K2 plus so on till 10 to the L, right? Here.
Yes.
Now, Fermat's little theorem says that 10 to the P minus 1 is congruent to 1 mod P minus 1 P. So
Okay.
even if I raise it to any exponent times anything, I still get 1. And now I can just force all of these to be divisible by P minus 1. So all this would be like 1 plus 1 plus so on till it's 1 mod P, which is equal to L mod.
Yes.
Correct? So all I need to ensure is Pi does not divide L plus I. That's another condition on L. Are we done?
I guess because
There's tiny detail left. There's tiny detail left. Both of these conditions, L is congruent to minus Si mod Pi, and L is not, L plus I doesn't divide Pi. Both of them have the same residue Pi. So CRT doesn't work right here. CRT needs all of the residues or the mod things to be pairwise coprime. So when you're writing up this thing, you want to ensure L plus I to be not 0 mod Pi. And L congruent to minus S of I mod Pi. This is equivalent. So, like, this is not always true, right? What if Pi actually divided S of I plus I minus I?
We can just choose large Pi. We don't.
Exactly. What if this happened? But there are way too many numbers. We can just
choose a good I, for example.
no. I is fixed. I is from 0 to 1.
PI.
Yes, good. We just choose large Pi. Like, just choose Pi bigger than N. This is obviously smaller than N. So that's it. Done. So I'll repeat the proof. So we had a lot of ideas in the starting, was trying to, like, shift the sequence slightly, trying to scale the sequence slightly, and to add a bunch of numbers to make the sum of digits slightly more handleable. Because directly it looks very weird. Like, right now we have no control on the consecutive digits sum digits. But a lot of arguments were very promising, but all just hinged on this tiny thing that all we just needed to resolve. How do we stop all of these divisibilities together? Just because they're divisibilities, and even if one prime fails it, we are happy. So this idea pops up frequently as well. You should just if you want to stop a divisibility, if you want to stop A divides B, you just choose a prime P to divide A and P does not divide B. This idea pops in pretty frequently. And if we can do this for everything, we are happy. And CRT does the rest of our job. We just need to be slightly more formal with our argument, but that's not the main part. Main part is CRT, the force CRT is very, very strong. So was the argument clear? Are there any questions? Is everything fine to everyone?
It's clear.
Great. I'll just wait for a few more if there's a few more some time because
Clear.
Yes, clear.
may
Yeah,
CRT
it's
be very
clear.
less.
So the basic idea is that most construction stuff is very weak and CRT is like too much
stronger.
stuff. Yeah.
CRT gives you way too much freedom.
CRT is just like, okay, give me these conditions, I'll merge them up for you. Just make
Yeah.
sure that the conditions are all like co-prime stuff.
Yeah.
And I'll do the rest of the work.
Exactly. So like if you actually try to find even L for like say 10, you'll reach like a million digits, something like not a million digits, but like L is like a million. So the A that you find also has a million digits. So
But we don't care.
but we don't care. They only care about existence. We literally don't care. We
Just
have
for pairwise co-prime condition, you just take it until some higher than some inequality, higher than some number.
yeah. So yeah. So CRT is very powerful. Now the second part of constructions is the wishful wish. What does this mean? So that sounds like niche, looks like niche, wishful wish. So basically, the CRT part of our solutions, like you see above solutions, look very rigid or very. They give less amount of things for us to work.
They're more
We
like
just
fixed.
exactly. They're more like fixed. You had a particular job to do, and and you just called CRT to do the job, and you just wrote down the conditions, gave it to CRT, and they did it to you. So this is more like the fixed conditions. Here, the harder part is going to be what to do. What should I ensure? So what you end up doing is you make a wish, like you observe pattern for certain things, and you say, if this were true, my life would be easier. If you could find something like this, I could solve the problem. So you just take this leap of faith, and it just works out mostly. So I have two problems which I was thinking. Both apparently use some fancy things. So
Oh, because we probably have some VP stuff, so
not VP. It's just
VP
like
no?
I'll paste no VP.
Okay.
But let's not spoil. I'll post both problems. Oh, when should I post both problems? Okay, I'll just post the second one. The first one, I just realized you did something weirder. Array, why is this not working? No. Size screenshot. Some people might have seen this before. So have a lot of people seen this?
I haven't
Has
seen
anyone?
this.
Okay. Has anyone seen this?
Neither have I.
No.
Okay, great. That's great. Try the problem.
Multiply by k, multiply both sides by k, I mean.
Yes, what do you say?
First, you can just multiply both sides by k.
Um, Multiply both sides by k, sure.
Oh wow! Immediately I'm getting like Dirishli vibes for some reason. I don't know why, but just feels like
Seriously,
feels
interesting.
like it. I don't know why.
So yeah. Let's wait for some time, I guess.
Is the problem's name wishful
Okay.
wish or you're hoping?
What?
Wishful
You
wish
want
is the idea. The problem is a problem.
Yeah, the wishful. Okay, so I divided constructions into three things. Let's just write it here. So I divided constructions into three things: the CRT force, the wishful wish.
This sounds very much like Christmas.
Wishful wish sounds like
It looks more
Christmas.
like a G than a C, to be honest.
Christmas gift.
Ah, sorry.
So wishful wish.
Good typoed while writing again.
Okay, bro. And the last, the impossible.
Very nice.
So this is actually, I have a legit example for the impossible. It's a solvable problem, but I have an example.
Is it a typo or like, what is this?
Bro, wait, where is the typo?
Impossible, the whole thing.
word.
I am more possible. क्या
I
लिखा
am
है
a
मैंने?
puzzle.
Sorry.
For
My
context, this is how Kanav types as well. I did not know that's how he writes as well.
sorry. This is why I failed boards. For context,
Wish
I'm
me
in
luck.
11th. I didn't fail boards.
Wish me luck at this rate for boards.
Good luck. Yeah. So I have a legit example for the impossible. So if we survive till that, we have chances. So I hope everyone gets the force of CRT, right? How powerful it is. That's fine. Now I just want you to wish, hopefully. So make a wish. Make a wish. So first of all, sequences are bad to work. You have subscript. Subscript is like so annoying to write. We convert sequences into functions. So that's just better. We write AI to be f of I. So what we want to ensure is that f of k, like plus 2f of 2k and so on, nf of nk is equal to 0. Yeah, now it's an FE. Like the problem changed from construct to an FE. Magic. Yes. So like the point is now I can do things like f of f. I can write f of f like much easier, right? Otherwise, I would have to write like AI. It's like disgusting. Better, bad. So sequences are just FEs.
So that is called g of x, g of x f of x.
Yes, let's define g of x with x f of x. We want to ensure g of k plus g of 2k, so on till g of nk is 0. N is a fixed guy here. K is the way. There are way too many conditions, right? Like if I list down every condition for every k, too many conditions. How do I reduce them? Because a function has way too much freedom. It's like literally I can pointwise choose a function, right? So again, I have too much freedom. I should be able to
And
utilize it smartly.
I think you
Would
get
it be
G is
possible?
cyclic, right?
G
I'm
is
not
cyclic.
sure, would it be possible to do stuff like ones and minus ones? Like that could simplify things a lot. Like choose a suitable choice of ones and minus ones for each
Yeah,
value.
f of x is 1, f of x, 2x is -1. It's like every two multiple will be negative and then something like that. Odd will be.
I see.
Can we just progressively generate it? Like we can start for some value of g of x and we can progressively generate it.
So the ideas somehow are similar. So you're trying to progressively generate with ones and minus ones, or like
Yes.
suitable numbers.
Yeah.
Okay, let's
But
try.
I don't know. N is equal to 2 does not work. I can't think of an example for n equal 3 either.
N equals to 2 does not
But
work.
like it might work. I don't know about n equal 3.
Yeah, so n equal to 2 apparently doesn't work. I'll just
Can you just show
how
the
do you prove
problem?
it?
The problem is just this: find a function so that this works for every k for all n.
No, it's like find all n such that there exists a function, right?
Sure, I just spoiled that, but never mind.
Okay.
Yeah, this is the problem.
Oh yes, because then we have infinity descending and infinity increasing, and they just don't work. Yeah.
Yep, that's correct. So for n equal to 2, things are not so nice. Look at mod 2.
Yeah, so then
2 divides f.
2 divides f of k and then 4 divides f of k, क्योंकि 2 divides f
Yeah.
of 2k and so on.
Yep. So like you can just say use f by 2 is f prime and then keep on repeating this. So 2 fails. So 3. Let's try 3. Yeah, that's a good thing. We can just try smaller
1
examples.
minus 1. 3 till 1 1 minus 1.
You get
Let
f
me
of
just
3
write one
to the f of 2k modulo 3.
1 second. Let me write down. Slow down, please.
Yeah.
Yes. Now say what you're saying.
Yeah, in this
1
case,
1 minus 1.
we get f of k
For
equals to
the 2k's, what if f dash doesn't exist?
we
Oh,
get
I'm
f of
sorry.
k equal to f of 2k modulo 3, which could be useful.
One at a time, guys. One at a time. Someone. Okay. Someone say now, and no one else will say. That's
1
a
1 minus 1.
1 1 minus 1. Okay, so 1 1 minus 1 is a solution, but I can't do that, right? If f of k is always 1, it can never be minus.
But you can also have minus 1 1, right?
Now,
So we can-
but yeah, so the issue is now you can do 3k, 6k, 9k, and it still has to hold.
Yeah. How do we do this? Your idea. This okay. I won't spoil it.
What
For
if
a minute.
okay, I know you said there's no v3, but it feels like doing stuff on v3 of k should be helpful.
Good. I'm saying this construction can be rigged to work. What he's saying can actually be rigged to work.
Mod 3.
Mod 3 is an interesting idea. So mod 3. So let's look at if you want to rig up this thing to work.
Like you could take like 2f of k is negative f of k mod 3 and then try to do some CRT, I guess. No, wait. So
Okay, so mod 3, what do you want to ensure? Let's slow down. So mod 3, you want to ensure that these numbers are minus 1. So one idea for f is like f of 3k is equal to minus 1 and 1 otherwise.
We can just have f of, we can just progressively generate it like this. For any number which is 0, which is not divisible by 2 or not divisible by 3, put anything.
Okay.
Right? For a number which is divisible by 3, f of 3x is equal to minus f of x. And for a number which is divisible by 2, f of 2x is equal to f of
the same
x.
thing.
Yeah.
Right. So what you're saying is f of 2x is equal to f of x and f of 3x is equal to minus of f of x.
Yes.
Right?
Yeah.
This should work, right?
Yeah, so I think, I got something similar. So I think what works is f of x is 1 if like v3 of x is odd and minus 1 if v3 of x is even.
Perfect. Yes. So this construction is equivalent to saying f of x is equal to, okay, I'll write it in a very fancy way. I want to do this.
Minus 1 to the power of
yes,
to the power
minus
3.
1 to the
Oh, wow.
v3 of x mod 2.
Oh, wow. No, mod 2
You
can be
don't need
mod
the
2 is
mod 2.
irrelevant. Mod 2 is irrelevant, my bad.
Wow.
That's the construction. Brilliant. So yeah, there's some very interesting things. So this is an explicit form which magically works. But the first part is the more interesting thing. So if I write f of k plus twice of f of 2k plus thrice of f of 3k, this thing I can just simply break with the rules that I basically gave f as twice of f of 2k, twice of f of k, my bad, it is plus 3 times minus f of k. Now, irrespective of the value of f of k, I just get this 0. So f of k just doesn't matter. Magically, I gave some very weird rules to f, and it just did my job. Does that make sense?
Yeah.
And now you should realize at this point, this should be generalizable.
So for even, we are done. For even greater than 2, I mean, we can just do first plus last minus second plus third. I mean, first plus last, second plus second last, third plus third last, and so on. We can just have them grouped.
Why is it not
So,
connecting? It's connected actually.
One thing,
I'll explain what he means. I'll explain what he means. His
Like
idea
f of
is
ik plus f of n minus ik.
So he was I and n minus I basically just want to pair.
one more thing, like the first
For
two, like 1 and 1 plus 2 and so on, is like just exactly the last number. So we are
What do you mean?
we
1
are,
plus 2 plus is exactly
like
plus one?
for any end of triangular numbers like 1, 3, 6 and so on. This
Huh.
just this same construction works because we can just put it. Yeah, we can just do the same construction for like 6, for example. No, no,
Yes.
no.
So a lot of these constructions are actually working. Can someone give me the underlying idea on what's happening? Like, what are the special things that we use in this construction and what's the general thing? It's a very intuitive thing that I'm saying, but
Number of ones equals number of minus ones.
not that.
I mean, number of ones.
Not that.
I feel like the fact that 3 is prime should be somewhat important here. Maybe. Because like the whole thing here is built on like v3 of x, and the idea on which this construction works is that f of 2x and f of x will basically be similar in the sense that they have the same v3, and I think this means we should be able to generalize this to all primes, because then f of kx will be like kx will have a different vp from px for all k less than p. So we should be able to do a similar construction based on VP of X, is my thought.
Right. So VP is turning, so there's this, I'll just write in a different color. So VP is important.
yeah, but n is equal to 4 also works. It's kind of sad.
Yeah, I was gonna say that.
Yeah,
This
it's
is
just
something. So there's a lot of things that's working, but we don't have a general structure, a general reasoning why everything is working. Oh, one second. Yes, sorry, my bad. So can you find a general structure which is common in VP, which is common in a construction with the left-hand side, the SF of 2x, 3x construction? What is some common structure between VP and that construction?
1 minus 1.
Not 1 minus 1.
No, it
Point
won't
is,
be 1 minus 1 because like odd primes, I think there's a weird thing where you do like p minus of p minus 1 by 2 to the something for odd primes if you try to generalize this construction. So I don't think it's just a thing about 1 or minus 1.
yes, it's not a thing. Another thing, I can choose 1 and minus 1 to be any coefficients, right? I can choose a very, like, all I wanted to, all the 1s and minus 1 ensured was that a plus 2b plus 3c turned out to be 0. Like, my bad, 1 plus 2b plus 3c turned out to be 0. That's all the 1s and minus 1 ensured. I can just choose any b and c and this should work out. So yeah, someone's claiming all out primes work, someone's claiming powers of 2 work. So so this must be some underlying structure.
We can basically say keep 1, 2, 3 may, or 1, 2, 3, 4 may 4 is indivisible by 2, and 2 is right. So we can have that. If we know 2, then we can, if we have a relation between 1 and 2, that same relation between applies between 2 and 4. Right?
Great intuition. So you're saying if I have a relation between 1 and 2, I should have the same two and 4.
And we can do that so on, right? So we can have if we have a relation between 1 and any prime smaller than n, then we have a specific thing. So we just have to show that we can decide something for the primes.
Precisely.
I am not sure what Shreyan meant, and please do tell me if this is isomorphic to what he said. But what I think might be nice is if we find some quote unquote base values which work. So for example, I think odd primes work, and someone said that 4 works. And you can try to somehow show that if some k works, then a multiple of k might also work. And then you'd be done, because like all odd primes work, 4 works. So then basically everything will like v2 not equal to 1 will work. And then you have like some very small cases left over.
Right. But they're still infinite, but small cases, sure.
No, wait,
Anyways,
actually
so,
there
yeah.
won't be leftover, because those will also be like divisible by some odd primes. So we'd be done.
Yeah, I guess even V2, yeah, V2 not equal to 1 will work. That's a like I got 2 raised to k should work except for 2x only. Like
Yeah. So
somehow I feel like that because for 4 and 8 is working. I don't know.
oh, 1 second again.
I think it would be nice to check if like 6 works.
1 plus 1, 2, 3, 4, 5, 6 is 1,
Okay.
2,
6
3.
So
6. If we get 6, then things will be a lot clearer.
Yeah, because 6 also has the thing that v2 is 1, but it also has the thing that it's divisible by an odd prime. So that might give us some good information
let's
if
try
we do
6.
6.
Let's try n equal to 6. I want f of k is 2f of 2k plus 3f of 3k plus 4f of 4k. My god. Plus 5f of 5k. Ooh. 6f of 6k is equal to 0. Wow. Oh, my hand's tired now. Okay.
So we need to figure it out for f of 2k, f of 3k, and f of 5k.
Right.
One thing we can notice is if we reduce it mod 2, then it looks very similar to like the k equals 3 case, I think.
Right, it does.
6 doesn't work here, I guess. I
It
don't
doesn't
feel
exactly work, but it's
The
quite
direct
similar.
argument doesn't work, but there's a lot of structure which is being preserved in some sense, is what you're trying to say, right? So
Yeah.
modulo 2,
Combine VPs of primes to get the conditions.
right? So another intuition came in, combine VP. So basically VP is turning out to be very important. What is so interesting and why is VP working? Why is VP working?
Because the relation between 2 and 4 is the relation between 1 and 2. The relation between consecutive powers of primes is the same. We can just have.
How do I say
Is
this?
that true
Without
though? Like, I'm not sure exactly if that intuition kind of checks out. I'm not sure. It doesn't
How
sound
about
like
this? How about this? We take f of k and then f of 2k you define somehow, like f of k times some constant, and similarly you let f of 4k and f of 3k and f of 6k be fixed हो जाएगा if we like choose that, and then just choose f of 5k.
Exactly. So what you do is you just ensure these kind of conditions. Something times f of k, f of 3k is something times f of k, f of 5k is something times f of k for everything. What this does, now just you can factor out an f of k. All your problem is reducing to some constants. The entire point of function just died. Now all you have is just a bunch of constants to worry about. That makes sense.
Sure.
Just choose primes to make it.
Yeah, and then you can work with like prime factorization and you get a diaphragm which probably works.
You just get 6 variables in one equation what you want to work out. Look, not 6 variables, in this case 3 variables and one equation what you want to work out.
So we get a lot of freedom.
You get a lot of freedom. Exactly.
We get too much freedom.
So what exactly happened? So what is the general idea that I was talking about? The structure that was
5, right? 5 has no other bigger multiples. You can just choose 5 to be negative times whatever there's other things sum to.
Yeah, I'll come to that part later. Solving the diaphragm I'll come to later. What I was telling is this kind of structure. This structure, why is this even related to VP?
Because we're multiplying primes and then stuff happens.
Multiplicative. VP is a very multiplicative structure. The conditions that we are seeing, f of 2k, f of 3k, is a very multiplicative condition. So, the main wishful wish that you make is Force f to be multiplicative. Multiplicative. I spelled that right, did I? Maybe I did. So you just force f to be multiplicative. You can literally just factor f of 3k just turns out to be f of 3 times f of k. So f of k just factors out from each of these factors. All you want to ensure is the initial things. Primes come into play because VP is literally a multiplicative thing. So if you force f to be multiplicative, the only freedom you have is f of primes. You can choose them to be anything.
So it's
And the rest of the
definitely, can't we just, it's definitely true if there is a prime which comes only once, like between n and 2n. N
slow
and
down
n
for that
minus.
part. Slow down for that part. I'll come to solving the Diophantine later. But is this idea clear on what the underlying structure was multiplicativity?
Yeah.
Yes. Yeah.
Now, from a very unhandleable condition, from a condition where we had no idea how to like build a path, we just threw all of this infinite condition into just one, right? So the wishful wish, which so basically, if you don't make this wish, it's very tricky to solve the problem. But if you just do this, your job is to just solve some random Diophantine equation. Is this part clear to everyone till now?
Yep.
Great. Now, the details. I actually just don't want to do this, but man, I have to do this. So yes, so someone was saying, so let's just try it for this case of 6. So what exactly I just want to ensure is f of 1 plus 2f of 2 plus 3f of 3 plus 4f of... Notice f of 4 is related
F
to
of
f
2
of
whole
2.
square.
Yep. Plus 5f of 5 plus 6f of 2 f of 3. Now someone said, like in this case, someone said, look at 5. So why 5? 5 just
Because
appears
like
once.
5 is free from everything.
5 is just free from everything.
Like you can basically arrange everything else and then f of 5 will just fall into place if you do
Yeah,
it.
and exactly. And f of 1 is supposed to be 1. So all you need to choose, if you can just choose f of 2 and f of 3, which are divisible by 5, like such that this remainder thing gets divisible by 5, you are happy, right? And you can just do that because you can just choose them to be 5. Haha.
How do we prove that there's always
but then
No, but
that's
then there's the
one.
1 at the start.
Oh, my bad. Sorry.
Yeah, it has to be like a constructor number, like k into k minus 1 by 2 for some first sum of first like k minus 1 numbers should be k into k minus 1 by 2 should be even. Like here.
How do we prove there's a prime between n and 2n for any n greater than 1?
That's
Why
called
do we need
Bertrand's
to prove
postulate.
that?
We'll be using this after the like for general thing.
Like
That's
f
called
of 5 f of 10 के बीच में है ना? F of 5.
Yes, that's the correct intuition. So I'll come back to
Wait,
this part
why do
later.
we need a prime between oh, so that it only shows up once. Okay.
Exactly. So later we'll come back to that. So basically, you can do this. You can just choose f of 3 nicely. Okay, choose f of 2 to be 1. Choose f of 3 nice enough. Make it work, okay? I'm not doing the detail. Or do you want me to do the details?
Please do the details.
I think we get
the... Yeah, like just choose f of 2 to be 1 and like you get 1 plus 2 plus 4 plus 3f of 9 f of 3 plus 5 f of 5. Now,
okay,
man,
sure.
It's fine now, right? Happy.
Yep.
Okay, so someone said, so 5, how do you generalize 5 if a prime appears once? If a prime appears once, nice, right? So what primes appears once?
Between
between like
n
and or like
n by 2.
a and
n by 2
a
and
by
n.
2 or whatever. Yeah.
N and n by 2. So if I can find a prime between this, that's good. And let's say there exists. It's called Bertrand's postulate. This is called, it's not postulate, you can prove it, but it's just called that. I don't know the spelling. It's, I think,
Was it unsolved for so long that it just became a postulate?
I don't know. I don't know the history. But it's not. It's you can prove it in elementary ways.
Wait, you can just quote what else for like anyone.
Yeah, you can prove.
Could you repeat what Bertrand's postulate states?
There's a prime between n by 2 and n for all greater than 2.
Oh, yeah.
Well, how
And
the
okay.
proof?
Gosh. Look it up. If you want. Okay, I know I don't want to do it. Like, consider this and then you do not
Yeah,
have
no,
prime
no,
fact.
I got it.
Yeah, whatever. Just don't. I mean, don't prove
Wait,
it and then just look
what
up
are
the proof.
those things? Two and
The way do you prove Bertrand's postulate?
Nee, but like how two and choose n and what is
Exactly. The proof is very clever. So the point is you consider 2 and choose n.
this? Okay.
And if you're trying to prove there's a prime between n and 2n, if there isn't, this doesn't have any primes between n and 2n, right?
Yeah.
And what you can show is that primes with bigger than 2n by 3 and n don't exist.
Okay.
And like something works out after this. I don't remember.
This is obviously like 2n by 3 is more than half. Oh, okay, that.
No. I'm proving from n and 2n, not n by 2
Okay.
and n. So this is
Yes.
some very, very clever proof.
Do we do something like
Yeah,
we
I am
assume
just not proving this right now. Let's just forget about this, assume this exists. So if you know prime number theorem basically says you can find infinite primes between n and 2n for all large enough. Not infinite, arbitrarily large. Between n and 2n, you can find arbitrarily large primes for large n. But let's just forget that. Yeah, let's just forget that. Thank you. How do we finish now? So is the prime p, which is bigger than n by 2, less than n. How do we finish? So all we want to ensure, oh my god. Yeah, there exists prime for all and at least 25. There exists prime between n and
How
6
do
by
you
5.
come up with 25 and why 25?
Bash and use pnt for the rest.
Oh, wow. Is that what modern math has come to?
I mean very big thing for solve using
Anyways,
supermasses.
let's just finish this problem. We're not much of left, right?
Okay, yeah, we
So-
have to do impossible too.
Impossible, I won't do it. I don't think I have time to do impossible. Yeah.
Can you just give it to us at the very least?
I'll give the problem. Yeah, give the problem. I'll ask you to try it. I'll bully you into trying it. Okay, so how do we do this? How do we finish? So this thing ensures I have a term of the form p f of p. F of p have total freedom. So I just want to ensure the remaining part to be divisible with p. How do I do that?
Well, you can just make all the other terms equal to f of k. So then it'll be like p 1 plus 2 plus.
The entire problem is there's a 1 in the start. F of 1 is equal to 1. So like the things look like 1 plus 2 f of 2 plus 3 f of 3 and so on. Like the one at the start just.
We can just make f of 2 equal to 100. Then we'll have 1 plus 2 plus up to p minus 1.
Nah, but there are things like f of 4 is actually f of 2 squared.
Oh. No, but since we take f of 2 equals 1,
Okay.
f of 2k equals f of k.
Yes.
So ideally we'd want to make f of quite a lot of stuff 1 or minus 1. Now.
So the general statement would just be like f of pk equals f of k for the second up to second largest prime.
Wait, can you repeat? What did you just say?
F of pk would just be equal to like f of k for all primes less than the largest prime, which is less than n.
Uh-huh. Why would you want to do that? Also, we just care about these p values, like not in general.
No, because then the sum will just be 1 plus 2, 1 plus 1. Okay, yeah.
Okay, I see what you're trying to say. So you say that the sum would be 1 plus 2 plus 3 plus so on till n minus p.
Yeah.
Right. But why
Oh,
should p divide this?
yeah.
So okay, 1 prime is not helping us. What do we do? Let's go back to the case of 5. How does this finish? Why does this finish?
Because like GCD of 9 and 5 is 1, so like you
GCD of
don't
9
have
and 5
any
is 1.
issue with like common multiples or anything.
Exactly. So
Also,
just working with 5 wasn't doing everything. I
Oh, so
needed 3.
you take like the largest two primes, less than
Yes.
n, and then you fix everything else to be 1, and then you get a linear Diophantine, I think.
Largest 2 primes. Now the point is, I know p only exists once. For most numbers, q would also only exist once. But what we can do
Q
to
can't exist a multiple of p times.
Like,
you can prove like very small bounds. So.
take 3 primes.
for primes, 7 like type of 7 types. I don't think 7 can exist.
Instead, you should just add another prime to the Diophantine.
Yeah, that's what they're doing. So we just choose 2 primes like this.
Maybe if p is a prime and p minus 1 is 0 mod 4, then it will work for all p.
Oh, okay. How do you do that?
Because by taking that the same sequence, like 1, -1 and all, like so you can construct some. So
I
p
see what you're
minus.
trying to say.
So using that.
Yeah, but okay, let's just finish this argument in general.
Okay.
Yeah. So like this is, so you can pick 2 primes like this. Now, the point is you would have p times f of p plus q times something, right? F of q. If you just have these 2 terms, you're done, right?
Yeah.
Yeah.
Everyone find why you are done. Because p and q are co-prime, so there exist linear combinations px minus qy equal to 1.
Then you can use diaphant.
Exactly. So you can just make any px z minus qy z equal to any z. And we were choosing integers, not positive integers. So that's one thing. So what if there's a 2q existing as well?
It's fine, no, as long as p is greater than 3.
Yeah, exactly.
So even if you have a 3q existing, as long as p is greater than 6, life is okay, you can finish.
Yeah, but then
The remaining part,
f of q square should not exist.
that's small cases. I'm not doing that.
Okay.
Yes, we are done. So that's homework.
Yeah.
Yeah,
Variable
homework is like
details
fast.
which you have to write up in TSTs. How fun.
Exactly. They'll make you do that.
Seems like a very hard problem to write down.
Indeed. Most of the solutions on thread are, this is horrible. Right?
It seems that for button possible consistency greater than 11K, there are more than 2 primes.
You can actually like for most n, you can actually have like just p and q occurring in n and n by 2.
Yeah, right.
Okay. So I'll just go through what we did again. So we proved n equal to 2 doesn't work, n equal to 3 worked. For this interesting construction, which for a long time we didn't need the word to describe, which was multiplicative. And the V3 coming in as well, also motivating multiplicativity. So basically the entire wishful part of the problem was hoping to set up equations like these, remove the variability of k, and hope for a very multiplicative function. This was basically the wishful wish that we made in the problem, which basically solved the problem. The rest of the problem is details, which is boring, annoying. Main part of the problem was the main wish. So is everything fine?
Yes.
Yep.
So we have 10 minutes, right?
We
By
can do the
default, it would have
impossible.
to be the last.
Yes.
We can do the impossible. Right.
The impossible is more like a joke. It's not. But okay. I'll just tell you how the impossible
Speedrun
is.
solution in 10 minutes.
I don't think that's shit, man.
Is this
Oh god.
no impossible in a nice way or impossible in a bad way? Like, is it bashy impossible?
It's solvable. It's solvable. It's just
but
I call it impossible for a reason. I'll just explain.
but is it bashy or impossible, or is it so
It's a
elegant
great
it's
problem. It's a
impossible?
very nice problem. It's a very nice problem. Read the statement and you'll like.
Wait, what's the source
Very-
of the previous problem?
Oh, one second. Let me just paste this new problem. USAMO 2012 P3.
Sorry, what?
One second, I just write it.
Wow.
Yeah. Okay, one second.
Somehow I
Just
feel I've
write it.
done this type of problem before, but I haven't.
So I'll just write it right here. USAMO 2012 3.
Okay, I just check it's a 35 more problem.
Why do you keep checking?
Wait, are P3s just supposed to fall apart like this?
It's USAMO. USAMO was
USAMO is approximately.
It's very old.
USM
like
is sometimes tougher.
I think the problem is tricky if you don't just get multiplicativity, basically. But yeah. Someone is someone is sending the Malaysian SST 2024 P7. I have not done the problem. So yeah. So you can try this problem. I probably it's a Malaysian problem, so it's probably very good quality.
okay. So in this problem, you can just combine the digits. You can just push the digits together, right?
Yeah, so this problem is completely brilliant. This is the part where it comes on the, I'll just write it, the impossible. Why is it called the impossible? I am a possible. And what do I write? So yeah, why is this impossible? Because of the statement, like read the statement. So basically you have some number, you can insert some like number 1, 2, 3, 5, 7, 8, 9, 4, 3, 2, 1, 6, 7, 2, 9. And I can insert plus lines like this,
The
like
easiest part
this.
is that it should work for all sufficiently large numbers. So even if you take Graham's number, it should work out.
It's like so brilliant.
What's
You can
Graham's
make
number?
single
Graham's
digit
number is like number so big that if all the digits are forced within the memory space of your head, the entire universe will collapse in on itself.
Okay, but how is it defined?
Check on Google.
Wait, will it
Hey,
still work if our number of digits is greater than 32?
You can, this will work anytime. It works for any number you say.
Is it because 9 plus 1? Is it because 9 plus 1, 10, 5 plus 2, or 5 plus 5, 10, 7 plus 3, 10 type thing? Like, is it basically.
Oh, yeah.
Am I
That's
missing
very
something,
tricky.
or does the
Wait,
number
are
just keep
you
decreasing?
But you need to make it 5 moves. Just 5
Oh,
moves.
wait,
5
how are
moves.
you
Oh, wow.
adding two pluses at the same time? You're supposed to add a plus and then add the numbers, then add another
No.
plus.
No, you first add plus signs.
Okay.
You first can add plus signs. Then this becomes 1, 2, 3, 5, 4 plus 8, 9, 4, 3 plus 2, 1, 6, 7, 2, 9. You add whatever this number becomes.
Because you want to make choices of the pluses, so after that there'll be many, many zeros. Something like that.
Yeah. Either you want there to be a lot of zeros, or you want there to just be a lot of very scattered out digits when you put pluses.
I
No,
think
you
we should
want
do
a
this in
lot of-
reverse.
You want a
I-
lot of zeros because if
5 is a
there's
very good number because when you take 1 and then you take 2, and you get like in terms of 2s and then 4s and then 8s and then the fifth term
I think
cancel most of the stuff.
I think we should do this in reverse. Like, we should see what numbers go to single digit in one move, and what numbers go to those numbers in one move, and what numbers go to those numbers in one
we
move.
can put how many plus signs?
You can move as many plus signs as you want.
Okay, get why you call this
You know
problem
what would be
impossible
funny
now.
if the problem was just wrong?
This is right.
Yeah, but
It
it's
feels
correct.
right. It feels right.
I was also convinced that the problem is probably wrong. Like, no way you can do it in 5 moves. Like,
What
it's
numbers
crazy.
can go to
What is it? Because 5 equals to 10 by 2?
The number is not bounded, right?
5 is 10 by 2. No, that's not true. I think you
Yeah,
can do
no.
it in 4 as well.
Okay, that's nice. The That means only one way question. this is possible is if we can convert it into many zeros. Without the zeros, this problem is impossible. Okay, so we have.
Right.
So we need to be able to convert it in. So let us look at what numbers can go to single digit in one move. Those are numbers of the form single digit, lots of zeros. No. Yeah, single digit, some zeros, another single digit, some zeros, another single digit, some zeros. And so that those single digits now sum to one single digit number, right?
Basically, lots of zeros. Loads of
Yeah.
zeros.
Yeah, you don't care about, you can just have zeros. You just care about having some, the non-zero. We care about the non-zero because the zeros we can just eliminate. And we can assume that the zeros came eliminated. Right? So we want to see what we can eliminate quickly. Okay, the final thing would be the number, the remainder when the number is divided by 9, because every thing is like modulo 9 preserving.
Yep. So yeah, so like it's like
This is
always
not
a
the-
fixed number. You can
Wait,
get.
so if you have like 33 ones in a row, so how do you convert that into single digit 5 moves? What would you add?
33.
Just add sign plus signs within the ones, all the ones.
So like you can just like go 1 to something like 9 and a 1, and then just add a 1. You get a bunch of zeros.
Easiest would just be 1 plus 1 plus dot 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 equals to 31. And 31 plus and
No,
31
not
is
all
3
ones. You
plus
just
1.
take a group of ones. Like
Yeah, but
for
easiest in
example,
this same case would be 31 ones ke liye.
that's
31
just a smaller case. I'm just taking like, what if I give 10 to the 33 ones? Then you have to do this.
10 to the 33 ones ke liye, I'll just sum up the ones and I get 10 to the 33. And then we have to
Hey, I'm just giving an example, bro. I give you 10 to the 10 to the 10 to the 33. And now what do you do?
That
Now
is
you
also the
just-
same thing.
Okay, bro, 10, like,
You just get
what I
a
basically,
with many digits.
you just get what I basically wanted. Okay, there is literally no time. The reason this is comes in the category of impossible is that there is obviously wishful thinking in every construction problem. But should I just spoil some idea?
No, don't spoil it.
No,
This
don't.
feels like it would be very
It's
sad.
brilliant. The statement is brilliant.
Fine, you can just try it then. What can I say?
I'll give you my Discord. Just DM the solution to me, if that's
Oh,
fine.
sure. I mean, yeah, you can do that.
Like, yeah, it's in the Zoom chat.
Damn, bro actually wants it spoiled.
Like if people like I can stay back for some time. People want to know why it's called the impossible and get slightly
Yeah,
spoiled in the
that would be
solution.
cool.
Yeah.
Is it possible to tell why it's impossible without spoiling it?
Not really. I won't spoil a
Is
big
it
amount of
like
the solution.
some of like elementary method or like some randomish thing?
No, solution is completely elementary. There's nothing fancy.
Okay. Okay.
And impossible is not because of difficulty. When I tell you, you'll understand. So if
Don't
people
tell us.
don't want to be at all spoiled with the problem, just want to try it because of the brilliant statement, I think you can just leave. Because
Solution
I'm not
is
going to do anything.
like something really stupidly easy and then, but really like weird.
Yeah. So if people don't want to get spoiled, you can just leave. I think I won't be doing anything. And thank you for attending. Yeah, you can mute. That works as well. If you wanted to stay back, you can mute.
Okay, wait, I'm staying and I'm disconnecting audio, so like put a message
Huh.
in chat when you're done.
You can do that. So if people don't want to get anything about the solution, you can just disconnect audio. So yeah, I'll tell in the chat when the audio would be back. Okay. And for people who want to just know why I called it the impossible. Yes, sure. One second. Sure. Yes. Okay. So has everyone who wants to not listen disconnected audio?
Silence is a yes.
Great. The reason this is impossible is that there is no CRT way or a concrete way to actually do it.
Okay.
So what I mean is that the solution wouldn't be concrete. Why? Because The digits are so crazy. I
How
can
do you
just make
practically manage to pull off something concrete? Right.
no, exactly. You
That's
just
the
cannot.
point.
You just cannot. Like because I have more freedom than you in this case. Like you're trying to put the
Right.
plus lines, I have far more freedom than you in this case. I can make the number so bad that any strategy of yours, I can just make it to fail.
Oh, so it's
Like look
kind
at this
of
as a two
it's kind of like local versus global then, in a sense.
kind of
Like
in
so
some
far
sense.
we were kind of doing local-ish type stuff. We were kind of constructing stuff algorithmically, that sort of stuff. Here, that sort of stuff isn't possible because like you can just make a really bad counterexample. So it should look more like a global solution in some sense, I think.
In some sense, that's a local global analogy. The analogy I was giving was a game. Like say you have Alice and Bob. The previous examples, you had more. Like if you were Alice and Bob is okay, say the game is between you and previous games, you had far more freedom. You were doing the main job. This case, I am doing the main job. I am giving you the bad number, and you just have 5 things to do. You just have 5 operations you can do it. I have the bigger job. So you just cannot really have a concrete strategy to make it work out. Does that make sense?
Third, don't we have more freedom?
Do you
than
have
the
more
other?
freedom?
Yeah.
Why?
I'll tell you. Because we can insert 2 to the n operator. Okay, first, in each step, we have less freedom, but we have 5 steps around, right? So it's like, I guess we can have more freedom overall. Because um, because originally he can choose 10 to the power of n numbers if it's n digits, and I can choose 2 to the power of n minus 1 operations on the first thing he.
It's not about the number of free choices you have. It's like
It's about
how
how
do I
limited they are.
exactly. Like if you don't, if freedom is not about how the number of choices you have, the control that you have is the freedom. It's like the number that will drop out after the sum, the number that you'll obtain after the sum. Do you have control on that? No. I have more control on that than you have. Does that make sense?
But we have control over the number of positive signs we are inserting.
That is true. That is true. But what I'm saying is the number that obtained, I have more control on that than you have. Does that make sense? Like it's very intuitions, like very intuitively.
Okay, yes. Yes.
So in some sense, you just cannot have a very concrete strategy working on. So let's break it as a one player game. So you found a good strategy. You give me the strategy. The amount of freedom I have, I can just wreck your strategy. Does that make sense?
Why? What if
intuitively, like because I can
From
just
a
make a
very
very bad
meta
enough number,
perspective.
right? Like I can just make a very bad number. Like I can choose as many digits I want. So if your strategy is to like find a 9 and a 1 consecutive and just add a 1 between, I'll just never give you a number with a 1 and 9 consecutive.
For an infinite number.
It's not an infinite arbitrary large, but yeah. But in some sense, so like, what if your strategy is like, I find a bunch of consecutive ones. I'll give you a thing which is no consecutive ones. I'll give you a sequence which is not even periodic, but only uses 1 and 2. Like, see the amount of freedom I have.
Digits of pi.
I mean, I have uncountably many choices.
No, you have countably.
Not uncountably. Not
Countably.
uncountably, but whatever. Countably,
No,
but like
actually,
way
yes,
too big.
uncountably, because it's like
It's not uncountably. It's not
power
uncountably.
set of n, but some stuff, sort of.
It's got power set of n. Power set
It
of n
isn't
is-
exactly,
is
but it's
countable.
uncountable, I think.
It's
not
countable.
uncountable
It's
either.
completely
It's
countable. It's the number of
countable.
natural numbers. The number of natural numbers is countable.
Yeah, it's
Oh, right,
it's
fair,
countable.
fair.
But the point is, I have way too many choices than you have.
Yeah.
Like I can just now are you convinced that I can wreck any of your strategy?
Yeah.
Yeah, I hated this.
I can just make a strategy that works for all numbers.
How?
I
Do
mean,
it.
bruh, like you can solve Riemann hypothesis as well then. Like I mean, this is not I'm not talking about a completely formal strategy. I'm just talking about some intuition on why should you expect which type of solution to work.
I thought you were
So in this case of
informal
problem, so you just cannot expect a counter, like it's just impossible for a concrete solution to work.
Pi's ultimatum.
And yet, this is in an anti-construct lecture.
Yes.
It
This is why I call the impossible. It's
feels
combo. It's a combo problem.
Yeah, it feels fun. That's why.
So the solution I'm not spoiling anymore. So basically, you just don't have a concrete thing. You need to do some kind of like a very variable-ish strategy. But figure that out yourself, I guess. So yes, is there anything? Is it fine? Why is called the impossible?
Yeah.
Yep.
Okay, now I'll just message on chat. Y'all can unmute now. Oh my god, I still typed it. Okay, I guess that's it. The source of this problem is some TOT.
Of course
Let
it's
me actually.
Of times.
Of course it's Russian. It just has to be Russian.
Yeah, it's Russians give nice problems. This is a nice problem.
Russians have incredibly slick problems for some odd reason.
They have nice problems. You mean nice. It's
Let me actually. Can I actually find out the TOT?
Russian and Iranian geometry is really good.
I've heard some things about Israeli number theory.
2010 Spring SA7.
Oh wow.
This is 2010 problem.
Yeah.
That old, okay. That's
2010 is not old.
2010 is
Wait,
not old.
am I the only guy who thinks that stuff before 2000 counts is old and after 2000 counts is like recent?
No, but Tournament of Time is like very
Before
old. Like
2015, I feel it's old.
I was doing
See,
1960
this
problem
don't
over
go
here.
ahead like telling to people about these words. I literally made up like yesterday. Like I was finding problems and I made these words up yesterday. So like there are more in the impossible like kind of problems, but these are my words that I just made up. I came up. Like these are all made up words. Okay, so I hope everything was fine. I hope you enjoyed, and that is it, I guess. Thank you for joining.
So basically, want a number which is
Thank you so
zeroable.
much. That was like such a great session.
Yeah.
Especially like the last part where everyone was on like audio mute and the
I
people
don't
who
know how
were
to
listening.
mute.
That was nice. And
Oh.
evidently the people who were on audio mute got that it was quite serious because
Yeah.
of the amount of hand taps that you were doing. So yeah, great session.
Thank you. Thank you.
Okay, bye.
Bye
Thank
bye.
you so much. Bye bye.
Thank
Good
Yeah, no
night.
problem. Bye
Thank you
bye.
for